So thank you so much for the invitation. So everything I'll talk about mostly will be joint work with Fernando Marquez, and then the end bit will also be joint work with Fernando and Evgeny Lukamovich. So I'll start doing a brief survey of a subject which has been at absolute core of geometry in the last 100 years, and in which Meyer has had an important result there. So I'll just do a very brief overview of the subject, and so naturally I will forget the name of a lot of people. So there's a very celebrated result with Burkhoff in 1917, in which it showed that every two-sphere, regardless of the metric you put there, you can always find a closed geodesic. And this result is important because the cheapest way to find a geodesic is by minimizing the energy function on a given homotopy class. But of course, every homotopy class, every curve in S2 is homotopically trivial, and so that approach will not work. Right? And so after this, then there was a long history of people working in the subject, and I guess it all culminated 8 years later with a joint effort between Franks, Bangert, but also Nancy Hingston, and they showed that every S2 admits an infinite number of closed geodesics. So you can do way better than one. You can actually find infinitely many. And so it's actually this was the hardest case for surface, and so it's now known that every surface, every Riemann surface you choose, for every metric you can find an infinite number of closed geodesics. So analog to the surface case, it's of course important to consider the general dimension case, and there the first result, this is due to Lushnik and Fett, and they proved that every manifold admits a closed geodesic. So they use the same method as Burkhoff did there. Okay. And so then the natural question is, well, if this result is the analog of that one, then is that an analog of this Franks-Bangert result? And the best one that we know so far is due to Gromol and Meyer more than 40 years ago. And the assumption is that, suppose that the manifold is closed, we'll always work with that case, and is also simply connected. So simply connected is the hard case to consider because there's no homotopy class to minimize. So what they showed is that if the Betti numbers for some field of the free loop space are unbounded, then you can find an infinite number of closed geodesics. So this condition is fairly mild. For instance, it's known now that it only fails for manifolds with a homotopy type of a compact rank 1 symmetric space. So the most famous case is the N-sphere or CPM. Right? And if one asks what would be the theorem for general manifolds, then the only thing one knows so far is that if you choose a closed simply connected manifold, then for almost every metric you can find an infinite number of closed geodesics. So this was proven by Radmacher some years ago. So it's a famous open question to find an infinite number of closed geodesics, say, on the tree sphere for any metric. Okay. So based on all these developments in the geodesics case, then one can do the same thing for a minimal surface, and this is what I'm going to talk now. So the motivation is that just like geodesics are critical points for the length functional, then minimal surface, they are critical points for the volume functional. And so Yao, he conjectured in 82 that if you that every compact free manifold should have an infinite number of immersed minimal surface. Okay. And there has been some progress on this conjecture, and so let me just mention 3 important cases, and then I'll mention one in 2 slides that I did with Fernando. So the first one is due to Simon and Smith, and so they show that every tree-sphere admits a smooth embedded minimal sphere. So then Pitts, but also Shane Simon in 82, they extended, so it's, I wouldn't say extension actually, because these were done both at the same time. The methods are, of course, similar, and these methods, they go back to Birkhoff's original approach. Okay. So Pitts, but also Shane Simon with the regularity, they show that every compact manifold admits an embedded minimal hypersurface, which is going to be smooth outside a set of codimension settings. So if the manifold, if the dimension is too high, then we have to allow for the minimal surface, minimal hypersurface to have a small singular set. So, and then so here, of course, the advantage is that there's no restriction on the dimension. And then Kahn and Markovich in 2012, they show that if you take a trimanifold, so which is hyperbolic, then it has an infinite number of essential surface there, and so you can minimize the energy in these homotopy classes, and so you can show that closed hyperbolic trimanifolds have an infinite number of minimal immersed surface regardless of metric. So the idea here is that there's a lot of topology in hyperbolic trimanifolds, so you can find these biminimizations. It's known that hyperbolic trimanifold will have an infinite number of closed geodesics regardless of metric. Okay, so three spheres tend to be the hard case because there's nothing to minimize there. So, okay, so I'll talk a bit now about this result there. How to get one minimal embedded hypersurface in a given manifold, and as I said before, the way to do this is inspired, of course, by the way that Birkhoff did it in the first place. Okay, so we have to do a bit of notation here. So I'm considering n+1 closed Riemannian manifolds, and I don't want to mention, I'm not considering the surface case, nor where the ambient dimension is too high. And so this space to loop, when we do geodesics, we look at the free loop space for minimal hypersurface. Then one reasonable space to look at is what's known the space of integral mod2 currents with no boundary. And so the right way to think about it is just the space of all compact hypersurface in the given manifold. So this space is well studied within the field of geometric measure theory. There's a topology you can put there. The space is compact with respect to that topology, and you know. So and then, as I said before, minimal surface, they are critical points for the functional which picks an integral current and takes its volume. Right? So the question is, how can we find out? And the basic principle, which was first understood by Birkhoff and then heavily exploited by Morse, the basic principle is that the topology of the space will force the functional to have critical points. So there will be critical points that have to be there because the space has topology. Okay? So this is the basic principle. And so the first thing one needs to know is what is the topology of this space. Okay? That's the crucial part. And this was done by Almgren in the 60s. And so Almgren essentially showed that any k homotopy group of this space, this is equal to Hn plus k of the manifold with coefficients in Z2. So what follows is that the first homotopy group is going to be Z2. So here we are always working within the connected component of 0. So the first homotopy group will be Z2, and every other homotopy group will vanish. And so a way of saying this is that the space is weakly homotopic to RP infinity. So at a coarse level, the topology of this space is as complicated as the topology of RP infinity. So in particular, we should have for every integer k some map from a k-projective plane into this space, which is homotopically non-trivial. Just like on RP infinity, if we take a linear k-projective plane, that will be homotopically non-trivial. So these maps exist, and we'll see a representative of this map right at the end of the talk. Okay? And so as soon as we have the topology, then we find the critical points. Of course, you could find using the gradient flow method, which would be using mean curvature flow, but it so happens that because of serious technical difficulties, the variational approach is more effective on this case. And so the variational approach works the following way. So we have our representative, we make a homotopy class out of it. So we just consider all continuous deformations of this original map. And out of this, we define what we call the K-width, which is the following number. So for each representative, I maximize the volume, and then I minimize among every possible representative. I think a good way of being comfortable with this definition, or with this number, which is might look fairly complicated at the beginning, is to think of what happens with the k eigenvalue for the energy functional, right? So if we want to find the k eigenvalue for the Laplacian on a compact manifold, then we will do the Rayleigh quotients, right? So what we do is we take a k plus 1 plane in W12, the space of functions, and then we maximize this scale invariant energy for this plane, and then we minimize among every possible plane. And so if we do this gives us the k eigenvalue. So we are doing here exactly the same thing. So we take, but instead of taking a k plus 1 plane, we take a k projective plane, and then we maximize the volume instead of maximizing the energy. But we can think of this as the nonlinear spectrum of the manifold. So I'll come back to this at the end of the talk as well. So that's why I put this in blue, so that we remember the definition. Okay. And so then, just like this number is realized by the energy of an eigenfunction, this number should be realized by the volume of a minimal surface. Okay. And this is what's known as the Almgren-Pitts minimax theory. So the theorem is that for every integer k, you can find an embedded minimal hypersurface with possible multiplicities that realizes these numbers. So the k width will just be the volume of this minimal embedded hypersurface. So on the face of it, it would look like we already found our infinitely many minimal hypersurface, right? Because for every k, we find a different one. Right? Now, the crucial point in the theory, which can also be seen in the problem of finding geodesics, is the multiplicity problem, right? Because from the point of view of analysis, there's no way of distinguishing between a geodesic and a geodesic wrapped 2 or 3 times, because they will both be critical points for a functional. And so the same thing happens for minimal surface. So for instance, it could be that all these minimal surface, they are just multiple of some given minimal surface. And so from the point of view of analysis, they are counted as different, but geometrically they are not. So this is the crucial point. So the crucial question is this set generally different, not counting with multiplicities? Right? And so here, 3 years ago, with Fernando, we showed that if we assume that the manifold has positive Ricci curvature, then indeed this set, they are generally different. And so the manifold admits an infinite number of distinct embedded minimal hypersurface. So what this says is that for the case of positive Ricci curvature, then at least Gauss conjecture is also solved. So our goal is to prove the same result, but without the word positive Ricci curvature there. We quite don't know how to do it, but what I want to explain is how we will do it, even if you don't know. Okay. So the reason why we have not been able to do it is that from the original theorem, there's no index information about this manifold, about this sigma k, right? So from the definition, we should expect that the index of this guy should be k, but that's not given by the theory. So the theory is fairly technical, and so Almgren-Pitts, they never proved any index statement about the existence of critical points. And so to be able to handle the general case, we need to have information about the index of minimal surface. That's exactly what happens in the geodesics case. Information about the index, accurate information gives you infinite number of geodesics. Okay. So let's just do a definition here. And so the index of a minimal surface is the number of different ways in which we can decrease the area of sigma. So for instance, we can consider here just the geodesics case. So we can think of this as being an ellipsoid, and I drew there two geodesics, this red one and the blue one. The red one, the index is 1, because if I move it inwards, then I decrease the length. The blue one, the index will be 2, because I can move it upwards, that will decrease the length, and I can also rotate, and that will also decrease the length. Okay. And so the theorem Fernando and I proved at the end of last year was that for every integer k, we can indeed find the minimal hypersurface sigma k, which has the property that the volume of sigma k is this one that realizes this min-max number, and the index of the support of sigma k is less or equal than k. So this is to be expected because this critical point minimizes in an infinite dimensional space and maximizes over a space with k parameters. So we should allow for k directions in which the area goes down and everything else, the area should go up. And with this general hypothesis, then this is the best result one can prove, because surely, even for the case of eigenvalues, you could use 3 parameters and get the first eigenvalue if they come with multiplicity. Right? Okay. So what I'm going to go through here now is I'll just explain the basic idea of how to prove this theorem. So what I will explain really is how would we prove this if we were in the case where the space of all currents, integral currents were finite dimensional, right? And then the real proof comes from going from the finite dimensional picture into the space of integral currents with this weak topology. So, but I'll just worry. So my goal here is to just give an idea of how does the proof start. So let's consider the case where k equals 1. So k equals 1 means just one parameter. So in this case, this representative phi 1, I can just imagine as being a curve like this. And the curve, let's assume for the sake of simplicity, that the curve goes through a critical point. This guy is a minimal surface there. And the way these arguments go is we assume that the index is 2, and we get a contradiction, meaning we find a better family which will contradict this min-max property of the volume of this guy. So I suppose I have this optimal family and that the index is 2. Right? So if the index is 2, it means that I have a 2-parameter family of deformations that decrease the area. Right? And these deformations come from ambient deformations of space. So I can apply these deformations to every surface which is nearby sigma. And if we do this, what we get is something like this, right? So here, this blue thing should represent the 2-parameter family of deformations that decrease the area of this minimal surface. And I can apply that to every element in the curve nearby, right? And so as soon as we have this, then because we only have 1 parameter on the black curve and we have 2 parameters on the blue curve, then we can of course choose a better path, right? And so the path will just keep going on phi as if nothing would happen, and eventually we'll get to a point where the area of this element is strictly less than the area of that element. And because on this parabola we have two parameters, we can go down, always decreasing the area, and then we can connect through here and then go back up and go down again. But the important point is that this map psi will have less area, so the maximum area of this path psi will be strictly smaller than the maximum area of the path phi, and so we got a contradiction, right? We contradict this min-max property because then we use psi as a competitor. Okay, so this is the basic idea. So the, of course, so now the goal, of course, is to start getting estimates from below, index estimates from below, and so to do this, one needs to avoid trivial counterexamples, as in what's known as the degenerate case. And so we assume the metric to be bumpy. And what this means is that every minimal surface is a non-degenerate critical point. So if one does the analogy of Morse theory, this is the same thing as assuming that the function is Morse. Okay. So if you take a metric which is not bumpy, you can check it a bit, and that will be a bumpy metric. Okay. And so in this case, we restrict ourselves to the case of one parameter, and we also assume that the manifold M has no embedded one-sided hypersurface, and that metric is bumpy. So this condition is fairly mild, right? So for instance, the N sphere satisfies, so something with CPN, of course, RPN would not satisfy. So for instance, if the fundamental group has no element of order 2, then this condition will be satisfied. Okay. So in this case, we can show that we can find a minimal embedded hypersurface with the property that the first number width is exactly equal to the volume, but now the index is 1. Before, we only had that the index was less or equal than 1, and now we can show that the index is 1, and moreover that the unstable components will have multiplicity 1. So let me explain what this statement means. So this statement means the following, that sigma 1, it could be some stable guy with some multiplicity plus a component of index 1 with multiplicity 1. But it could not be a component with index 1 and higher multiplicity, nor just a component of index 0. Okay. So what I will do now is I will explain the basic idea how to rule out multiplicities in the case of one parameter. And the biggest question now in the area is how to rule out multiplicities in the case of two parameters. Okay. So I will explain the key idea. So let me do a picture here because I couldn't fit it there. Okay. So the setup is as before. So we assume we have this path. Let me do it like this. This is my path 5. This is phi of 0. This is phi of 2. And now this is the maximum. And for simplicity, I assume that nearby the maximum, I will always see a surface with multiplicity 2. The general case follows from always put ourselves in this situation. So, but for the sake of simplicity, let's just understand why this cannot happen. And what I'm putting here is that suppose that this guy would be 2s1, and every element here, so every element from here to there, is some surface. For instance, this would be 2s1 minus epsilon. This would be 2s1 plus epsilon, right? And every element there is some surface with multiplicity, right? And of course, we also assume that from s1 minus epsilon to s1 plus epsilon, going through the minimal surface, that this is exactly the deformations that come from the fact that the critical point has index 1. Okay? So, which is saying this. I assume that the areas of all these guys is always smaller than the area of this. Okay. And same thing for all these guys. So now so the key remark is I want to go from here to there, but in a way that the area is always below this element. So the idea is simple. So the way to do this is usually I never attempted this, but I'll just say what's the best visual way of managing this. So we can imagine that in going from here to there, you're like jumping over a hurdle with both feet at the same time. And what we want to do is do the same thing, but just put one leg at a time instead of doing both legs at the same time. So we leave one guy, and then we can go from 2s1 minus epsilon up to s1 minus epsilon plus s1, right? Where we leave one leg fixed and we just move the other and we go up a bit. And then we go from s1 minus epsilon to s1 plus epsilon, where now we pass the other leg. And then of course we can do the same thing on this side. And so we go here from s1 plus epsilon to s1, and then we go there. But the important property is that this path, the guy of highest volume is below this one. So in some sense, embedded minimal hypersurface with multiplicity should have infinite, the index should be infinite. But of course, unfortunately, we don't know how to make this into concrete things. Okay. So now I will talk about this min-max approach to prove Yao conjecture, at least in the bumpy case. So the conjecture we have is that if we assume the metric is bumpy, then unstable components that appear in min-max hypersurface, they will always have multiplicity 1. Okay? So the previous theorem just shows that this conjecture is indeed true when we have only one parameter. Okay? So when the dimension here is important, because if n equals 1, which means that it's a surface, then a student of mine found examples where you can get multiplicity in the unstable case. On the other case, the surface case is much different from the. So for the purpose of the theory, there's a big difference between minimal surface with multiplicity and geodesic multiplicity. And one way in which we can see the difference is the following. So if you give, let's compare the equator with multiplicity in the 2-sphere and the equator with multiplicity in the 3-sphere. Nearby the equator with multiplicity in the 3-sphere, there's a lot of minimal surface that are collapsing onto this minimal surface multiplicity too. Okay. So, and they are all embedded. Near the equator on the 2-sphere with multiplicity 2, every other geodesic is immersed. Okay. And in the conjecture and in min-max theory, we always get the existence of minimal embedded guys, so we cannot get this. We cannot get just one great sphere and tilting the other two, as we could in geodesics. Okay. And so what I will explain now is that making the bridge with Toby's talk yesterday morning. So in the mean-curvature flow, there's also similar conjecture called the multiplicity 1 conjecture by Tom Millman, where it says that the blowups will always be multiplicity 1. And so in spirit, they have the similarities. This conjecture, if true, it would imply the Yau's conjecture, and this is what I'm going to explain now. So there's a result, so there's a future coming result that I'm doing with Fernando, so this is about to go up very soon. And we show the following, that assuming multiplicity 1 conjecture, meaning that multiplicity does not appear in unstable components, then for every k, you can find an embedded minimal hypersurface sigma k, which has the property that the index is k, unstable components have multiplicity 1, well, this statement will just follow from multiplicity 1 conjecture. And these guys realize the k width. But now, from the fact that we know that the index is indeed k, then we know that the supports have to be all distinct. Right? And so one consequence of the theorem module of multiplicity 1 conjecture would be that for every manifold, if you put a bumpy metric, then for every integer k, there is a minimal embedded hypersurface whose index is exactly k. And so this would give a stronger version of the conjecture.
So just to be clear, in that theorem there, your version of multiplicity 1 conjecture is verbatim with the opposite of the insertion of that bumpy matrix?
Yeah, that's right, yeah. For bumpy matrix, that's right. That's right, yeah. So that's right. So this would prove Young's conjecture for bumpy matrix. That's right. That's right. But on the other hand, so yeah. That's right. I would expect this to be true for matrices which are not bumpy, but the degenerate case is always a bit tricky, so let me not make. So okay, so we're gonna shift gears now, and we're gonna go back to this nonlinear spectrum idea, or which is to go back to the analogy between this K width and the spectrum of the Laplacian. Okay. So Gromov, he calls this the nonlinear spectrum. So let's just recall the definitions. So the definition is, for every integer k, we take this phi k. So let me just write this so that we know what phi k is. So phi k is just a map from some k projective plane into this space. So we take the representative, we consider the homotopy class, and then we maximize for the given representative and minimize in the homotopy class. So Gromov, he calls this sequence the nonlinear spectrum of the manifold. And the reason why he calls the nonlinear spectrum is in analogy with the Laplacian spectrum, right? Which is also given by a Mimax definition. So Gromov in the 80s, and then Good extended considerably Gromov's work there. They figured out the growth rate for this nonlinear spectrum. So, and they showed that omega kf grows like k to the power 1 over n plus 1 as k tends to infinity. And so, in the result with Fernando, that we show that for positive Ricci curvature matrix, we have infinitely many minimal embedded hypersurface. We use this Gromov good result because we distinguish the minimal hypersurface there by making sure that the areas, the volumes of their support cannot all be just a finite number, and we use the growth rate to...
Is this a one-sided or a two-sided bound?
It's a two-sided bound, so maybe, yeah. There exists some constant, which depends on the manifold and the dimension, where omega k over k is less than or equal than c and greater than 1 over c. Two-sided bound. Yeah. We will see later where the upper bound comes, at least for the sphere, because that already has content. So usually the lower bound comes from the vanishing lemmas. So comes from the power structure that one has in the cohomology of this space. Okay, this was a thing that Gromov observed, but somehow it didn't fully exploit it. And then Larry exploited heavily this power structure on the cohomology ring of this guy to get the lower bounds in an axis. So the lower bounds come from topology, the upper bound is from geometry, a representative. Okay, and so. Now, keeping back with the analogy with the linear spectrum, there's a famous theorem due to Weil and the Weil law, which states that the growth rate of the k eigenvalue is universal. So this limit is universal up to the volume, right? So this limit will only depend on the volume of the manifold and nothing else. Okay. So this is one way of thinking of of course, this theorem has had a profound impact in lots of different parts of mathematics, and what also will be very redundant, but what it's saying in some sense is that as k is large, every manifold is a ball, at least for the purpose of this number, right? They all look, they all have the...
That's a different omega.
Yeah, oh, that's right. Yeah,
Standard.
that is right, that's right, yeah. Yeah, so this is the volume of the n plus 1 ball, not the n plus 1 of the manifold. I should have used that. That's right. And so Gromov, he conjectured that these numbers, they also satisfy a phi law. So that as k goes to infinity, this limit should just depend on the volume of the manifold. And so with Lukamovich, Fernando, and myself, we confirmed Gromov's conjecture. So Lukamovich was a postdoc of mine at Imperial, and he's going to move into MIT, I think, starting September. So, so what we show is that the phi law holds, meaning that we can find a universal constant such that for every compact n+1 manifold, and now we allow for the case where the manifold may have boundary, then the limit of these numbers will just be a universal constant times the volume of M, and then to the appropriate scale invariant power. I guess, so I will say some words about the proof. So we'll put this out even before the end of this month. So we follow the basic approach of, so we follow Weil's original proof of the Weil law, right? Which amounts to, you have a region, you decompose into various subregions, in which case you know what the spectrum is, and then you infer from that things about your original spectrum. On the other hand, in Weil's case, he could compute this constant optimally because there were examples in which he could compute all the spectrum, like for instance on a disk, right, or on a sphere. In our case, I think it's fairly puzzling to us that we were able to prove this without knowing what the optimal constant is. So now, what I will explain now will be what our guess is for what this optimal constant, for what this constant is, and in doing so, we'll also see where does the upper bound come from. Okay. So I guess a crucial question is, can we estimate this number there? Because there's no single case in which we can compute the nonlinear spectrum for every possible integer k. Because as k gets large, it gets really complicated. So let's try to estimate this when n equals 2. Okay? And so if I want to estimate this, then I might as well just put here M to be the 3-sphere, because the limit will be independent whether it's a 3-sphere or any other space. So let's might as well work with a 3-sphere with a round metric. Okay? And so we need to find competitors to get the upper bound. And one way of doing this is to look at all spherical harmonics on the 3-sphere, which have degree less or equal than this. So it's known that these will be homogeneous polynomials of a certain degree, and so we assume the degree to be less or equal than d. And then we take the span of this. So this is a finite dimensional vector space. Now, on this vector space, we make the following equivalence relation where we identify a polynomial with its multiple, just like we do it when we define the projective plane. And so if on this vector space we remove the origin and we identify a polynomial with any multiples of itself, then we get some k projective plane, and of course k will be d minus 1, or no, sorry, k will be, so the dimension of this space is not d. It's some large number which we can compute, and actually it's d cubed plus d, okay? So, plus 1. So, if we do this, we get a k projective plane, and the dimension grows like d cubed. So, k minus d cubed is a lower order term. I think it's d. The real dimension, I think, is d cubed plus d. Okay? So, this is some projective plane of dimension roughly d cubed. Okay? And now, out of these spherical harmonics, we can construct our competitor. And the way we do this is, for every element there, we know it's a polynomial, and so we just take its zero set. Right? And of course, when we do this, it does not depend on the representative we choose, because the nodal set is independent whether I take the polynomial or twice its polynomial. The zero set is the same. Okay. So this would be A family. Right? And then we can use Crofton formula to show that the element in this map, the element of highest volume is bounded by 4 pi times the degree d, which Yeah, it's just a hypersphere with multiplicity. It's just equated with multiplicity. So knowing this number and that number, then we can compute the quotient and see that alpha 2 and see that a comparator we get is this number 48 over pi the square root of the cube root of this. So we get that alpha 2 for sure is less or equal than the number we get from this family. And so the question is this charm? We would expect that asymptotically this family would be the best one, and that we can do this on any given manifold. You take a manifold, you look at the eigenfunctions, the first k eigenfunctions, you do the span of that space, you look at the zero set, and we'd expect that asymptotically that should also be the optimal family, but we have no idea.
What about the lower bound of tensor topology? Is it way off from this?
So the lower bound here for this family is easy to see because you take, let's see, you take dq balls, so you take d balls of radius, I think one over cubic root of k or something like that, and then you know that it's a polynomial of degree d, so you'll have an element which will cut these d balls. That's the ham sandwich theorem, right? If you give d regions in space, there's a polynomial of degree d that cuts these regions and let they have the volume. It's called a ham sandwich theorem. So that's the thing that good is always using extensively. Okay, so it comes from this, right? And this happens for any general sweep out. You have a k sweep out, it means you take k regions. There's one element which cuts these k regions exactly half the volume, and so we can estimate the area there by the isochromatic constant, and then we can do some computation, then we get the thing. So it's coming proving these estimates.
Okay, but it's a much smaller number, or?
The lower bound.
The lower bound that you would get that way for, I mean, alpha then you don't.
It is by a factor, yeah. By doing that, right. Then becomes a problem of tessellating the sphere, right? What is the optimal way in which you can cut the sphere in k regions so that each will have the large isochromatic constant? There are also, so if you do on the two sphere, the best way would be the honeycomb division, but it fails by a factor. Yeah, that's right. If you do in S3, I think the problem is no. What's the optimal tessellation of S3?
So I mean, the sort of surprising thing is that you're saying that you prove without knowing what alpha n is, you prove that there's such a limit, not a lot of limits.
That's right. We prove that the limit is independent of the region without that's right. So I'll give you the data. That's right. Okay, so let me explain just the basic approach, and let's restrict ourselves to the case where M is just a subset of space. So this is just M and lies on space. In particular, it will have boundary. So the approach is to do like Weil did it to prove the Weil law. So first we find disjoint cubes all inside M, which almost give every volume except for a tiny region, right? So we put here a cube, here another cube, another cube. And so we do it in a way that what we miss will be small. And so then using this cut power structure of the cohomology product, we can show an inequality like this, which has that the k width divided by the n plus 1 root of k is greater or equal than this average sum of the ki width of each cube. But now this is the unit volume cube, and it's the weighted sum because the weight is its volume of this cube Ci, and here this integer, the width we take is exactly the integer part of the k times the volume, right? So, for instance, the smaller cubes, then we'll get a small number there, and the bigger cubes will get a number comparable to k. But this partition is fixed, right? As soon as we have an inequality like this, then the lower bound will follow. Because now if we take the limit here, the cubes are fixed. Then if k goes to infinity, ki goes to infinity too, and so we get that the limit there is greater or equal, this now is a constant, that the limit of these regions, and because this guy is almost 1, we get that the limit for the region is greater or equal than the limit for the cube.
So now it becomes crucial that you define these omega k's for manifolds with boundaries, right?
That's right, that's right, that's right.
So, but you just take the cycles to be relative cycles?
That's right, yeah, that's right, that's right. Just like, actually, Gromov and Good, they always work with relative cycles. So just with Fernando, then we will start working with cycles with no boundary, but yeah, that's right, it's crucial. So we do relative cycles, so we just consider cycles and we say two cycles identical if they differ by an integral current which is plotted on the boundary. And so from here we get that this limit is greater or equal than that one, and now we want to get the reverse inequality. Of course, this is exactly what Weil did to prove the Weil law, but he had the huge advantage over us, which is that he knew how to compare this number, and so Weil, well, what he did was, he did cubes which approximate from the inside, cubes which approximate from the outside, and then because he knew the exact value, he could get it there. So we cannot do this, and so we reverse the process, which is we now take a cube, and instead of stacking cubes inside M, we stack scalings of M inside this cube in a way that we almost take all the volume. So we start putting here copies of M with different scalings. This will be the Mi. And again, we can do this so that we miss just a small region. Okay.
So
And
do you actually work with pieces of M with boundary or something in order to put them inside?
So M, I'm just assume that it's a region with boundary. So piece of M with boundary. What is it? So M is just a region of space.
Yeah. So you really reduce it to the case with a region with boundary, and rather
That's
than
right.
the entire manifold to put it
Yeah,
inside.
that's right. So the manifold case, I'm not going to do it here, but there we have another idea.
Oh, I
So-
see. I should have read the top
Yeah.
line. I'm sorry.
So we figured out this right at the beginning of the year, and then it took us a while to figure out how to do
I see.
the case with boundary. So we do it by way of breaking the manifold into various pieces, which you can put in space, and then each time you have a sweep out of the space, you can break the sweep out, put in the regions, and go back and forth. Yeah. So to handle the case with no boundary, then we don't do it like that. We have to do something else. Okay. So, but the point is that when we prove inequalities like this, the only thing we are using is these ham sandwich type theorems, or another way of saying is it's the cohomology structure of the space of integral currents, and so it doesn't matter if I do MC or the reverse inequality, right? So I could replace here M by C and there C by M, because the same proof would work. The proof is combinatorial and topological, right? And so if I reverse the approach, which is now I stack copies of M inside the cube, then I get exactly the opposite in inequality, and then we can show that the limit, and then we show that the limit, so this shows that the limit is universal, and then a bit more work shows that the limit equals the limit cube. Okay, so we can actually do that. But this is the basic idea, okay? So this finishes my talk, but before I'll do it, I'll say that in the last 4 or 5 years, there has been a lot of work on these variational aspects of minimal surface, and so I will just do a brief shout out to all the young people who are working on this area, because they have produced now retrospectively a really nice body of work here. So I'll just go through some of the most significant results proven by young people in the area. So all of these results, they come from, so the intuition for all these results is to do an analogy with either the geodesics case or the spectrum case. Okay? So Shinzu, he showed that he studied one parameter min-max for positive Ricci curvature. In particular, he shows that in this case, the width is always attained by a minimal embedded hypersurface. The motivation here is a result of Calabi and Cao, which show that if you have a sphere with positive Gaussian curvature, the width is attained by a simple closed curve. So this is the analog of that Calabi result. Then Montezuma, he constructed a min-max hypersurface which intersect a given concave set. So the motivation here was a result by Bangert, where he showed that if you have a surface and if you pick a concave set, then you can find a geodesic which goes through that concave set. Then Lukumovic and Glenn Eddy, they found universal bounds for the K-width. So we know that the K-width, as goes to infinity, right, it grows with the power K over 1 n plus 1. But if you pick any given width, for instance, like the 7 width, it's possible that if you change the manifold, then that 7 width could go to infinity, even if it's asymptotically or not. Right? So they gave universal bounds for this, assuming the manifold is conformal to a metric, assuming the metric is conformal to a metric with positive Ricci curvature. And these, they were inspired by a previous result of Nick Carvar, where he shows universal bounds for the K eigenvalue, assuming the manifold, assuming we are in a conformal class of something with bounded Ricci curvature. Then Kentover and Shinzu, they also studied the min-max problem, but for self-shrinkers. Here the connection is that self-shrinkers can be seen as minimal surface for a different function. And so one can try to do the same approach for this scenario. Then Kentover, he also studied, he gave optimal genus bounds for min-max in the surface case, meaning for three manifolds, when we do min-max with for surface in a given three manifold. Then Charles Nurser and AX, they computed the first 9 width of the 3 sphere for their own metric, and AX did a similar thing for the 2 sphere. And so to give you an idea of how hard this is that to compute the 5th width, it's equivalent to know the our solution to the Wilmot conjecture. So the solution of the Wilmot conjecture plays a role in computing the 5th width. So to compute the 10 width, you will have to use some trivial things there. Okay. Then Marco Guaraco, he did min-max for the Allen-Kahn equation. So there's another way of obtaining minimal surface, which is considered the Allen-Kahn equation, and obtain them as the limit of an interface of solutions to the equation. And Guaraco did this by considering index 1 solutions to the Allen-Kahn equation and looking at the okay, this is also a very promising area. So Antoine Somme, he showed that the least area minimal surface is always embedded. And again here, the motivation was from a result of Calabi, who shows that the geodesic of least length on a surface, on a sphere with positive Gaussian curvature is always simple. Okay, so this has a motivation from the geodesics case. Then there's been some very important work, but because it exceeds the length of the slide, I couldn't fit it all. But I'll just say that compactness properties for minimal hypersurface with bounded index. So the motivation here is that from min-max, we know that we can produce minimal surface with an index control. Now the idea is, how can we translate the index, which is information about some Schrodinger operator on a manifold, how can we construct that, how can we translate from that into topological information about the manifold? Like, are the Betti numbers bounded? Can the manifold degenerate? The surface degenerate? And so here there was a compactness result by Sharp, then Buzano-Sharp, then Carlot also had some interesting result there. Then Shadosh, Ketover, and Maximo, they looked at the three manifold case, and Lee and Zhu, they also looked at the three manifold case. And then finally, Beck, Hanin, and Hughes, they study min-max families given by nodal sets of eigenfunctions. So they show that if you look at the first k eigenfunctions on a given manifold, if you take their span, and if you look at the nodal set, they show that that's continuous in the flat topology and that there's no concentration of mass. Okay, so I'll just stop here.
Many thanks for the nice talk and for the overview. Are there more questions?
If metric is not bumpy, can one get a lower bound in terms of tonality?
Well, that's what one would expect, right? That's right.
Is that
So I can get in the one parameter case, yeah. In the one parameter case, the theorem is if the metric is not bumpy, then the index is greater or equal than nullity. That's right. So we show the thing we show is that the index is greater or equal than nullity.
What's the difficulty?
Nullity plus, say it again.
What's the difficulty in general?
It's the multiplicities. The multiplicities is to look how things degenerate. It's multiplicities, yeah.
So when you used a hypothesis of positive Ricci curvature before, it was just
Okay, then why might I use that? Because when you have positive Ricci curvature, this tells you that this minimal hypersurface, this min-max hypersurface only has one connected component. Okay. And so now, if the K width were all multiples of that guy, then the area would grow linearly. But I know from the Gromov good that it has to grow sublinearly, so we reduce that. Say it again. Yeah. So the Almgren, it's tricky for the following reason. So the Almgren pits for surface give the existence of a minimal embedded surface, but for geodesics it doesn't give the existence of a closed geodesic. It gives the existence of a network, and so you could have things with triple junctions, right? And so and so now it's a conundrum. It's like this: either you can work with this space, so this is the space of one currents in a given manifold, and the advantage of this space is that the topology is well understood. So the topology is so weak that the topology of this is well understood. Okay, it was done by Almgren. But then you work with this space, but then you get networks. On the other hand, you can work with the loop space, but then the topology is infinitely more complicated. And so you do get closed guys, but then the topology is considerably more complicated. Yeah, I had a student. So initially I thought that we could do something with geodesics. I had a student working on that, but then I realized that it's definitely more subtle than I thought. Geodesics problems is dependent on it.
So, no further questions, and thanks.